Okay, then we should be live whenever live streaming on Assumptions of Physics. And let's see that everything sets up itself. Okay, so we should be on. So first, a piece of news. While reviewing the stuff that we saw last week with a mathematician, we actually found a fatal flaw. So a lot of the stuff that we saw last week actually just doesn't work, and which means I have to sort of re-go through everything and understand which pieces survive and which do not. And so it will be, I will need to do that before we can keep talking about that stuff. So today I have a bit of more foundational work that's gonna survive because it sort of mimics something that already exists in the literature. So we're gonna go through that today. But then we'll probably need to figure out what else to do in these lives because there is a lot of stuff that I have to figure out, and it's probably going to take a lot of time. So yeah,
Um,
that's how research work. You do something and then you realize that it's all wrong, and you go back from scratch and you have to redo it. So
um, are you really live? I can't see it live right now.
say it again.
Are you really live on YouTube? I can't see it be live there. Maybe maybe my YouTube is glitching, but
Oh,
I don't see it live stream.
let me double check that because that's more important. Okay, let me see. Uh, Let's see. Here says that I'm live.
Okay, maybe it's my YouTube glitching. I don't know. I can't see the stream right now. I mean, I see you, but not on YouTube.
Yeah, let me check.
I don't know. I can't see the stream right now. I
I
see. Okay, then it's my end. Okay,
yeah, I see it. I see it because yeah, no, it's working. It's working.
and that's fine.
Okay. Well, always good to check. Okay, so let's look at this stuff. And this stuff, it's something, it's one of those things that I rediscovered, and only afterwards I learned that somebody else did something very similar decades ago, and so on. The foundations of physics and quantum mechanics, a lot of it is like that. Everything gets rediscovered and over time, over and over by different people. And yeah, so even the whole thing of convex spaces, it seems to have been something that has been rediscovered and rediscovered. I don't know. It's a mess. That's how it works. So, what we're going to discuss right now sometimes are called orthogonality spaces. Sometimes they're called polarities, but the whole point is sort of to mimic something that happens in vector spaces. In vector spaces, when you have an inner product, you have a notion of orthogonality. And with this notion of orthogonality, you define the subspaces, right? You basically look at all the things that are a span, and then things that are live in a different span. They're going to be orthogonal to each other, and you find these orthogonal subspaces. And it turns out that you can basically not even know that you are in a vector space, not even know that you have a vector product, just know, given two vectors, whether they're orthogonal to each other. And that's enough to recover a notion of subspaces. And so there is a construction that you can do based on this idea, and this is what we are going to use in the ensemble spaces to find subspaces. And even more important, in for us, we want to recover, let's say, points in physical space as being sort of a limit of a support of ensemble that becomes smaller and smaller and smaller. And for that, you kind of need the whole set of subspaces with the ordering relationship of which subspace is inside what subspace. And so you can find this a nested sequence of subspaces and then sort of say, oh, those are going to be the point in space, the points that sort of support the distribution, right? Because we're going to start with the notion of ensembles and recover the points. And so we need a construction to recover these points. And uh, and so we are going to go through this construction. This I am guaranteed that it works. And it's kind of fun because it's one of those things with very few assumptions you can construct a lot of structure, which is always what I like. So if that's clear enough, we can start. Here we present a generic construction that we'll be using in a couple of different ways to construct lattices of subspaces. The structure we're going to define is sometimes called orthogonality spaces or orthomodular space, and it sometimes appears in the context of Galois connections. The general idea can be understood by looking at vector spaces with an inner product. The inner product defines a notion of orthogonality between vectors, and this notion of orthogonality can be used to construct subspaces in the following way. If we take U as a subset of the vector space, we can define the set U orthogonal of all vectors that are orthogonal to all the elements of U, right? So you take a set of vectors, all the things that are orthogonal to all of them. This will return the subspace orthogonal to all elements of U. And then we can also define U orthogonal of orthogonal as the set of all elements that are orthogonal to all the elements of U orthogonal. So you do the thing twice. The set U orthogonal will contain all the elements of U because they are all perpendicular to all elements of U by definition, but it will also include all the elements in the same subspace. If U were a subspace to begin with, then U would be equal to U orthogonal. We can now proceed in the opposite way and just use the relationship of orthogonality to define subspaces by looking at the sets for which U equals U orthogonal of orthogonal. Right? So instead of knowing what the subspaces are, you just know that there are two elements that they are orthogonal. And then you can create this construction. What are all the elements orthogonal to a particular set? You do it twice, and you get the subspace that contains the elements of the original set. The construction works, maybe we can put an S, for any binary relationship that is symmetric and irreflexive. For example, given two distributions, the fact that they have disjoint support is a symmetric and irreflexive relationship. Our distribution does not have disjoint support with respect to itself, and the order of the comparison does not matter. We can then construct subspaces based on this relationship and find the set of functions that are all defined within different regions. So you start with a distribution that has a support. Then you say, give me all the distribution that have disjoint support. So you're going to get the set of everything that is not, that the support does not have an intersection. And if you do it again, you're going to get all the functions that whose support is within the support of the original function. And these are subspaces in the space of functions, because if you get the inner product at being the integral of the product of the two functions, well, that's going to be zero if and only if they're going to have disjoint support, assuming that, again, we are using functions that are integrable and always greater than zero, like probability distributions. And so we recover this notion of orthogonality and of subspaces just by knowing whether two functions have the disjoint support or not. So it's kind of very powerful. Very minimal initial information that you need. So in our case, separateness as defined by the mixing function or orthogonality as defined by the entropy are symmetric and irreflexive, and therefore we can use this relationship to define notions of subspaces. Now, one of the things that it's a little bit tricky that I do think that I have a solution, but again, we need to review everything based on what happened last week. If you just take something that is separate, something that it's symmetric and irreflexive, sometimes this lattice of subspaces that you get, you get it, but it's not very nice. And so the question is, what extra conditions might you need to have something meaningful, physically, reasonable, and so on. And it is probably that this idea of being able to do single decomposition in terms of mixtures of convex combination gives you exactly the nice lattice of subspaces, because that's what happens in classical mechanics, and that's what happens also in quantum mechanics for measurement context. Now, whether this is necessarily sufficient, I don't know. But the point is that this is just the very minimum of what you need to do this construction. There might be other things that needs to be done and defined. Okay, so if that's basically what we're going to do, and so we start by essentially assuming that we have one of these symmetric and irreflexive relationship, and see what we can construct. So we start with the generic set X and a symmetric relationship that is A R B, then B R A, right? So R here is a relationship. You can think it as R would be the orthogonal symbol or any other symbol that you can put between two elements, and then you say they have this relation. So we define the R complement, the UR, of all the elements that are related to U, and study some useful property. The symmetry of the relation is already enough to recover most of the property we will need. Okay, so let X be a set and R is a symmetric relation. Now, the relation mathematically is basically a set of pairs. So if you have an equality is a relation, you have a set, you define an equality, and then you have, or an equivalence, and then you know whether two elements are equivalent, means that they are inside the set of pairs defined by the equivalence. So this is how it works at a set theoretic level, how they're typically defined. Given a substitute U of X, we define the R complements to be U R equals all the elements in X, such that for all B in U, A has the relationship with B. So if this were orthogonality, this would be all the elements in A such that they are orthogonal to all the elements in U. And now with just this, we can show a bunch of different properties. So let X be a set and R a symmetric relationship. Then we can find that this is it's not monotonic. It flips, right? So if U is a subset of V, then the R complement of V is a subset of the R complement of U, right? And again, if you imagine with orthogonality, if you have something that is inside a bigger subspace, when you do the complement of the smaller subspace is bigger than the complement of the smaller subspace, or the bigger subspace. And this is essentially how it works. So suppose that A is inside the R complement, then by definition B is for all B in V, A is R related to B, and since U is a subset of B, that this should be a subset equality, not strict. Okay, it is also true that for all B in U, A is related to B, and therefore A is in the R complement of U by definition, and since A was arbitrary, the R complement of V is a subset of the R complement of U. That's how it works. Another thing that you can show is if you do the R complement twice, you get a set that is bigger than the original set. Now, I do not know whether it makes sense to go through this proof, and to be a Mark, you can tell me what you want to do, because they become how can I say? They're not complicated, but it requires a certain effort to go and see, because you always have these things that bounce back and forth. So it requires some time to go
Mm.
and look at these. So I don't know whether it makes sense to go through them. And
Mm.
if you
If you think the time is spent better elsewhere, then let's skip them. It reminds me a bit of like rejecting like this looks like the law of excluded middle where it's rejected or not always true, right? The U subset URR. That's like the double negation thing
Yeah,
almost.
yeah. So, and again, it's all a property of that is just a lot of it is is going through the definition and apply. Like, you
Mhm.
know, there's
Yeah,
stuff like this, and you need to make sure that whenever you're doing the step, you are, you know, set theoretically doing the right thing. And I had a student actually go through this pretty thoroughly, so I'm not so worried about the even though that there was still a subset there that should have been a subset instead of a strict subset. But I basically don't think that if there are mistakes, you'd be able to spot them just by looking them through. That's more.
yeah.
So
Okay.
that's the problem. So, okay, so what you do have though, that if you do the R subspace, the R complement of the R complement, you get something smaller. And again, you can intuitively understand because of what we said before, right? If you have your function on some support, you look at everything else, everything that you had before was already by definition something that was orthogonal to everything else, or they had disjoint support with everything else, right? So you can prove that, and that's basically how you do it. What you can show that it's even more useful is that if the R complement of U is equal to U R complement of the R complement of the R complement. Like, so if you do it three times, the two of them go away.
Yeah, that also reminds me of double negation and triple negation.
Yeah, exactly. And but you're not like you're not it's like when you typically have the you don't have the law of excluded middle, that you can define a negation and you find that the double negation is greater than something, but then if you keep doing it you get the same thing. So it's basically the same as that.
Yeah, exactly. It's nice.
And then the other thing that you can show, which is a consequence of these two, is that if you take the R complement of U, that is equal, and this is equal to the R complement of the R complement of V, then you can switch things around. Then the R complement of the R complement of U is equal to the R complement of V. And again, you can see this, how it descends from here, because if you just put an R complement on both sides, then this by this would become only one, and so you can keep going back and forth. Another thing that it's important is that the R complement of the union is equal to the intersection of the R complements. And again, if you think of subspaces, this is basically telling you that the orthogonal complement of the union of some subspaces is equal to the intersection of the orthogonal complements. And this is true for intersection, for union that becomes an intersection. It doesn't work the other way. So if you put here an intersection, you're not going to get the union. So there is a specific way of how this works. And then the other thing that, of course, the R complement of the empty set is just the full set. That's it. So
Yeah, all of that is very Boolean.
yeah, yeah. It's going to become something like a Boolean algebra at the end, but not quite. So this is only needed the symmetry, actually. Like the nice thing is that all these properties are already there because of the symmetry, of the symmetric nature of the relationship. And then the last two properties, which are actually needed to be able to actually be able to talk about subspaces, come from both the symmetry and the irreflexivity. So now we have X that is symmetric and irreflexive. What you find is that the intersection between U and U are and the U complement, and the R complement is the empty set. And let's see. And this is because it is not true that for all B, so that basically means that one element can't be in both since it's a reflexive, something is cannot be orthogonal to itself, then it can't be on the R complement. That's basically how it works. And with the fact that it's irreflexive, the R complement of the full space is the empty set because again nothing has the relationship with itself, and so if you take everything and you say what is the set that is orthogonal to everything else, it's going to be the empty set because every element is at least does not have the relationship with itself. It's not orthogonal to itself, and therefore it's not going to be in the complement, right? So these are the two things that essentially stem from the fact they're symmetric. So now that you have this property, you can now define a notion of R subspaces by requiring that a subset is the R complement of its R complement. And then we can construct the lattice of subspaces and show that it satisfies property we would expect from a lattice of subspace. That's how it works. So if X is our set and R is the relation, then if U is a subset of X, the R closure of U that we note like this is going to be the R complement of the R complement. And so this is again the idea that you take something and you create a subspace over it. And then an R subspace of X is a set U such that it's equal to its own closure. And then the lattice of R subspaces is the set of all the subspaces that are ordered by the inclusion. Okay, so we basically have you have a set. You can define whenever you have a set, you sort of can make it bigger to make it something that is closed under this this double operation. And then you have the set, all the sets that are going to have that property that they don't grow up once they're already closed in some sense. And you order these by inclusion. This forms a poset, a partially ordered set. And now we can show that that partially ordered set is actually a lattice. And this is the proof. So the corollary is that the lattice of R subspaces is a topped intersection structure on X, and therefore is also a complete lattice. A topped intersection structure is a particular order theoretic structure. It's a set of sets where the intersection is always there. And then given two sets, you always have a sort of a bigger set that contains both. You have a supremum, so you have a join in terms of the lattice operation. So the set L, the lattice, is a collection of subset of X, and that's given. Now let's take an empty family of a non-empty family of those sets. Then using the definition of subspace and the fourth and fifth properties that we've proven before, we have you take the intersection of all these sets. And then since by definition there are subspaces, so by definition they're equal to the closure of the complement of the complement. So you take this and now they're the complement of the complement. Now this is an intersection of some sets. Now you can make this being the union of the complement. And so you get this. Now you do these things where you double it up so that you put a complement of the complement because you know that it's going to be the same thing. And now you take these two and use again the fact that you have this relationship between union and intersection. And then what happens is that you re-get what you had at the beginning with these extra two R's outside. And so this it tells you that this is actually a subspace. And so since this is a subspace, it's inside the lattice of the subspaces, which means you can always make an arbitrary intersection. And this basically means that this is enough to show that this is an intersection structure. And the everything that you need is that you have the complement of the empty set is the complement of the full space is the complement of the empty set, which is the complement of the full space. So the full space is a subspace. Therefore, it's inside, and therefore there is a maximum to the whole structure. And of course, there's also going to be an empty set. Therefore, this is a topped intersection structure because there is a top element. And this is a standard result that a topped intersection structure is a complete lattice. And that's basically it. So that these things form a lattice like you would expect. You know what? I do have problems here in the streaming. This thing is not. Let me refresh.
Yeah, it's still not showing up for me. I just see the one from 13 days ago.
Okay, I'm very confused because I'm not getting. Huh.
Same for me, actually. I don't see a live stream.
Okay, so it's not on my end after all.
Oh crap, that's not good. Did I screw up then? Because there's absolutely no activity on the chat, right? So if anything, if anybody's looking at the live stream and it seems to work,
Maybe
please
it's
put a comment on
private
the
or
chat.
something. I'm not sure if live streams can be set to private, but maybe that's what's going on. Then nobody would see it because nobody got the notification.
I did.
Even if I go into the channel, I don't see.
Yeah, exactly. That's
Okay.
why I'm looking.
What? It says privacy unlisted. You guys are right.
Yep. So that's the problem then.
Why was it an... Okay, is it public now?
Let me refresh and see. Not yet. Ah, yes, actually. There it is. I see it now.
What a disaster.
It's not that big a deal.
That's fine. I guess, well, it should be recorded, so hopefully
Yeah,
we
it
can
does
always...
say that it has 27 minutes of history, so it's not like stuff is gone, I think. It's just basically showed up late for people.
Okay. Okay, well, okay. So yesterday when I did, I prepared everything. I must have taken a different public setting. Okay. Oh, well, sorry about that. So now I see two concurrent viewers. Okay. Oh, well.
Do you want to reintroduce or just move on?
I don't know what to do at this point. I am a little bit like wow. Let's just go through it, and if there are people, I don't know if people are. So usually, what happens is that I make, I prepare the thing, right, and the people also get notified that there's going to be something and so on, right. So if people were expecting to join, they probably they didn't see anything before. They might have looked for something at half an hour ago, and they might have not have seen it. So I don't know how many other people are going to join anyway, because they're probably going to
Yeah.
have said, "Oh, there's nothing," and then that's it. So I assume that what's going to happen is that they're going to see the recording afterwards. And
Mhm.
apologies for the mishap. So I think we just continue. And if there are people that join, they can always ask in the chat what's going on. So yeah. Okay. Well. I'll be and now I know where to look. In the the studio setup, there is a privacy that before said unlisted and now it says public. So
Mhm.
next time I'll make sure that that thing because everything else said live.
Yeah, technically it was live, but you'd
Technically it
have
was
had
live.
to hand send out the links.
Yeah, exactly. Okay. Well. Oh well, oh well, oh well. Okay, so it's also true that it's this is going to be the end. So if we can always redo it if people join. But anyway, let's go through this and it's going to be a weird live today. Okay, so we have this top intersection structure, which means it's a lattice, meaning that there is a biggest element and a lowest element, and we can make joins and meets. So we take two elements, and you can find the biggest thing that is smaller that is smaller than both, and this is the meet, this is the join, the bigger the smallest thing that is bigger than both, and then you basically have it's essentially a Boolean like structure. It also has, in this case, this also has a complement because the R is going to be the complement. And in fact, I'm not even, that's something that should be here.
What is
Interesting. Uh, so it's more than this. So you know that it's a lattice, but then you have the complement, and you should be able to prove that this is actually a Boolean algebra.
yeah, and it's like the by taking the R closure, you're basically making it so that's the equivalent of setting lem to true. So because then you get the excluded middle, right?
Yeah, yeah, it's
Without that,
exactly.
you wouldn't get it.
And let me put this as I guess, as a conjecture.
I mean, that should be a really straightforward proof
Yeah,
by just going through the definition and going, yep, that's that, and that's that.
yeah. We are complement as the complement. I mean, that's kind of the name already implies that
Yeah,
that's
I mean,
gonna be it.
the relation is not, and then the union and neither, the and or basically, and that's all you need, I think.
Say it again?
The relation, the R relation is not, and the union and neither basically and or, and that should
Right. So
be everything.
the union is not so the join is not going to be the union. That's the only thing that is going to be different, and that therefore they need to be checked.
Okay.
So it's not going to be a Boolean algebra of sets,
Yeah. Okay.
and it should become. This is something that. Yeah, so no, it's not going to become in January that, but yeah, in principle, you should still have the complement, and you should be that you basically need to check the distributivity of the lattice. That's basically the thing.
Mhm.
The basically, let's put it here. Begin proof. Check distributivity. If it's distributive, then it works. I actually do not know if it's distributive, and it might not. because of what I said before. Right. So if this, it might be that for distributivity, you also have it. You need to have it in the other direction. That the right, because of De Morgan, right? So the intersection, the complement of the intersection should be the union of the complements. So it might not be a distributive lattice, and that's where it wouldn't be a Boolean algebra.
Is it like half distributive, like left or right distributive? I don't know which one is which there.
Oh yeah, yeah. It's gonna be one of those. It might be one of those. Yeah, yeah. Okay. If anybody joined again, sorry, I had the stream set to unlisted instead of public, so it was a disaster, complete disaster. Okay, so we have that are so we have a lattice, and it's going to be a complemented lattice. It might not be a distributive lattice, and so yeah, complemented lattice it should be is complemented, and then algebra. Okay, so that's basically it. That's a simple exercise actually to check those things. Okay, then what happens is all topped intersection structure actually are have a closure. So all these topped intersection structure actually come from a closure operation, and for every closure operation, you have a topped intersection structure. So there is a very intimate relationship between the two. So what is a closure in terms of set? A closure is something that the closure of a set is bigger than the set. Then if it's a set is a subset of another set, then the closure is bigger than the closure of the smaller set. So it's monotone. And then the closure of the closure is the same thing. It's a idempotent. So whenever you have a set operation that increases the size of the set, cannot decrease the size of the set, it's monotonic and it's idempotent, that's a closure operation. And if you have a closure operation, if you take the sets, all the sets that come out of the closure, they form a topped intersection structure. That's a general result of order theory. These are the type of thing where I would like at some point to create a sort of a bare minimum of what you need for order theory that would have some of these things there that are sort of things that are interesting to know, but also that are kind of useful for us. And these we can prove because they're very easy. The first property is true by the second property of 174, or I can even click. Right? If you recall, whenever we had a set, we make the complement of the complement, and then we have something bigger, which means the R subspace is always bigger. Then this, using the first property of 174, we have that if U is greater than V, then this implies that the R complement of V is a subset of the complement of U. And then we do it again, and we switch it again. So that the complement of the complement of U is a subset of the complement of V, and therefore the subset of U, the closure of the subset, the R closure of U is a subset of the R closure of V. And then the fact that it's idempotent comes from the fact that we can take that whenever we have a bunch of complements, we can remove two. So now when we do the closure of the closure, we have 4 R complements. We can remove 2. We only have 2, so we get only one closure. So this is nice. The proof of this is very simple. And then. What are these? These are just other proposition. So this is going to be the smallest subspace of R subspace containing U whenever you do the closure. And whenever you have, if U is a complement of V, then the complement of U is equal to V. So that you have this dual property between when you do the complement with respect to subspaces. And again, the proofs here are very simple. We can even go through that. So if you have something that it's a subset of X and V is inside the lattice, such that U is a subset of V, then what you have is that V is going to be greater or equal than the closure of U. And since U is a subset of V, using the second property, we have that the subspace of U is greater than subspace of R, which is also V. Therefore, V is a subset of the closure of U, and the closure of R is a subset of V. Therefore, they're the same thing. This means that no R subspace that contains U is smaller than the closure of U. Again, these are things that you would expect intuitively, but you have to prove because because they might not be wrong, right? Sometimes things that you think are intuitive, they actually turn out to be wrong. And then the last thing is suppose that you have two subspaces and U is equal to the complement of V, then it's also the complement of the complement is equal to V. And then what happens is that you do the R complement of both sides, and this, because this is a subspace, is equal to V, and so therefore you have switched the R in the two places. So that kind of how it works. And lastly, one thing that you can do is show that if you have an inner product space and you define the R relationship to be orthogonality, that is, two elements are related only if they're orthogonal, then what you find is that R is an irreflexive asymmetric relation. And again, because if you have two elements, nothing is orthogonal to itself, so it's irreflexive, and the inner product is symmetric, so this is going to be a symmetric relation. Then you're going to find that the R complement is exactly the orthogonal complement, because you are going to be defining the orthogonal complement is the set of all the elements that are in the whole space that are orthogonal to all the elements, and therefore this is going to give you the same thing. And then you're going to find that the R closure of U is the closure of the span of U. And this is essentially how subspaces work. So you have that the R closure of U is going to be the complement of the complement, which returns the smallest subspace containing U, which is going to be defined by the closure. Well, you find that it's the closure of the span of U. So that's all I have for today. I don't have much else. As I said, we can discuss what would be useful to do for the next lives, because as I said, like I need to review a lot of stuff, and it's kind of a bummer because I thought that I was done with a significant amount of things so that I could start actually writing papers, and now I can't write papers. I have to go back and work on this. So if you guys have any idea of what you guys would you like to see, or has anybody in the chat that has ideas of what they'd like to see for next time, I'm all open for ideas.
So what was the big issue you ran into, you said at the beginning?
The big issue was that the thing that I thought was a good property on measure actually turns out to not be true. So if you remember, I said that the measures that we wanted had this property. Yes, that if you take the measure of an open set and you make it on the closure, you will get the same value.
Mm-hmm.
And it turns out that that's not the case. So you can, I think I have the
So then
comparison.
the closure might not be zero measure addition, basically.
Yes.
Okay.
It is only true for a certain subsets of open sets. For example, it should be true for all regular sets, but it's not. There you go. Let mu be the big measure on a real line. Then there exists an open set such that the measure on the open set is different than the measure of the closure. So what you do is take the Smith-Volterra Cantor set, or also known as the fat Cantor set. So you know how for a Cantor set, you take the set of points from 0 to 1, and you remove the middle third.
Mm. And do you shrink the middle to zero, but not quite or something, and that's the issue?
So what you do, instead of taking the middle third, you take the middle fourth.
Fourth. Oh, okay. That's enough. I thought you
Okay?
have to even smaller than that. Okay.
Right. So now what happens is that since you're taking every time a fourth out, when you make the limit of the measure, it's not going to go to 0, it's going to go to a 1/2. And so now what happens is that you have a set that is generated, essentially, you can think it as the complement of the union of the countable union of open sets. And therefore, it's going to be a closed set. It's a perfectly valid closed set, and it's going to have a measure 1/2. But what's going to happen is that if you take now the complement of the interval from 0 to 1 of that, so you take the set of 0 to 1, open set, and you remove this set that is closed. Now that thing is going to be an open set, and when you make the closure, you recover the full interval between 0 to 1.
That's measure one.
So the boundary is empty, right? So the boundary of U is empty, and you make the closure, but still you're able to make the measure go up.
Yeah, that's a classic issue with the monster functions and stuff.
Yeah. So basically, this sort of discards a lot. There probably are a lot of other pieces hidden in there that are gonna still be valid because they weren't relying on this property. Like there is a way that I was making the limit to recover the measures that it's probably gonna still be valid. And so I have to do all the work to go through all the definition and all the theorems and understand what has to be kept and what has to be thrown out. So
or refined.
yeah, I need a different definition because we still need a compatibility between the measure and the topology.
Yeah.
And at this point, I don't know exactly what it is. There are these things called the regular open sets that might provide a key thing. Regular open sets are basically open sets that are the interior of their own closure. So
Okay. Yeah.
if you imagine this set, right, this U is definitely not the interior of its own closure
Yeah.
because you take this, you take the closure, you get 0 to 1, and now you make the interior, you get 0 to 1. So this is not a set that it's interior of its own closure. And it's very likely that those are going to be the sets where the boundary is going to have measure 0. And when I do the lattice of subspaces in the construction that I suspect that all these sets that I get there are regular open sets, which means that since those sets generate the topology on the point, it might also mean that all the spaces on which we want to have the probability distributions are going to be spaces that whose topology is generated by regular open sets. And these already have a name. They're called semi-regular. And so it may be that, again, I'm gonna have more constraint that comes from just the physics. So I already noticed that not on all topology we were able to define um, probability distributions. So that still is true. Like that result still is true. And so it might be, for example, that you need a topological space that is whose topology is generated by its own regular open sets. But again, I don't know. Like at this point, I really don't know. And at this point, I really want to do it carefully because I spent too much time writing even the text between proofs and so on, and that's all time wasted at this point, right? Because
Mm.
because it really was not. Yeah. So I'll probably take that section, bring it down, and leave the pieces that I know that they were that are still safe, and I need to do all of this week.
It doesn't sound fun.
No,
Ah,
it's not fun at all. Also because I thought, as I said, I was happy. Oh, that writing stuff now I can start writing papers
yeah.
because the funding is we say that we're going to publish papers, right? So
Mm. Yeah.
so, yeah, so that's the problem. I
Regular
mean,
open sets.
that's why it's research, and effectively, it's complicated because we're trying to tie in. Ideas from a million things. Like I'm not, I studied some measure theory. I don't have everything super,
Mhm.
so, and again, I was even looking at this with another mathematician for like 3 times we met, and only the third time he started saying, "Oh, wait a minute, there's something that doesn't smell right here." And so he found another problem, a smaller problem. And at that point, when I finished talking to him, I said, okay, well, that problem is not so debilitating. Maybe I can still work around it. And then I found this. I said, okay, no, this I can't
What
do.
was the other problem?
The other problem was, oh, yes, that we had this claim for the nicely bounded set. Let's see. Let me just look for it. And nicely. Is it?
Right, I sleep on it.
There you go. This is not true. The fact that the closure of an nicely bounded set is the closure of the interior, this is also not true.
For the same reason, I feel, right?
Yeah, it's the same reason. Yeah, of course.
Yeah. Okay.
And in the proof, basically, we said that something was equal, and it wasn't true. Like it was just inside. It was not unequal. So this proof is wrong.
Yeah.
These are still true. So it's still true that the nicely bounded set generate like form a Boolean algebra, and there
Mhm.
is a Boolean algebra generated by the open sets, and it's a Boolean algebra of nicely bounded sets. So that's still true. And I can't imagine that that's not significant because but it doesn't allow me to prove the thing that I wanted to prove.
Yeah, I think that second condition that fails up there, that's basically if you go to the regular open sets, that means it's true by definition, right?
Yes.
That's
Yeah. So again, the regular open set form also Boolean algebra.
Mhm. Yeah.
And that Boolean algebra is, it's again not a Boolean algebra of sets because the complement is the exterior. It's not the complement. Like it's not the Boolean complement, the set complement. It's the exterior. But again, you still have a Boolean algebra, and that Boolean algebra is going to be embedded in the Boolean algebra of nicely bounded set. I suspect that if you take the Boolean algebra of nicely bounded set and you quotient by essentially the sets of measure zero, or some proper set you might get the everything, right? So
Mm.
there might be like a nice relationship between the two algebras. I just don't know. That's what I suspect because there were too many things that with this mistake and with this thing I was able to prove things. So I assume that there is a way out in terms of using those concepts and maybe some, but I still don't know. And again, I suspect that when I do the subspaces, I do get the algebra of the open sets, and so there must be something. The thing that I haven't found uh, I know, but maybe look. Oh, there you go. This is gonna be the piece, all right? So if I say, that's okay. I think I figured out something. So if I say I have a topology that is generated by the regular open sets,
Mhm.
and I define in some sense a pre-measure on those regular open sets, they are a Boolean algebra, so I can define a pre-measure on those things. Then I will be able to extend that to all the Borel sets because since the regular open sets generate the topology, and then the topology generate the Borel sets, then I have a pre-measure on a Boolean algebra that generates all the Borel sets.
Okay.
So that's how it works. Okay. Okay, this is gonna work then. Okay, so this is only gonna work if my topology is generated by the regular open sets. Interestingly enough.
I mean, it makes sense to me that those would be the ones that matter because
Yeah.
stuff like that, Cantor said that's quite exotic. That's
Okay. Okay. You see there was always. It's funny because I go from these moments of like complete deep, oh, I'm not gonna be able to find, and then the idea comes and said, oh, actually, this idea is very reasonable and
it's nice to see a eureka moment on camera.
yes. Now, okay, so this is gonna work. This is gonna work, right? Because I already have the hunch that the sets that I have are essentially the subspaces are regular open sets. But, I mean, this you can even see. So suppose that I have like an open region of phase space, right? Now, if you take away a point in the middle, right, what happens is that that's not going to be a regular open set. Because now if you get the closure and then you do the interior, the point is going to reappear, right? Because the point inside is a limit point. So when you make the closure, it's going to be inside. And then when you take the interior, then you're going to find a set that contains that point. Okay, so good. So, like physically, what it means is the following. If I have if you imagine that I have a probability that has a support that is non-zero only on that open set, right? So it's a probability that goes up and goes to zero in that point. Now, if you take the set of all the things that have the support that are disjoint, you get all the probability distribution that are outside, and then you take again the probability distribution that are disjoint from all of those, you're going to get also the probabilities that have a non-zero value to that point. right? So when you're making the closure in terms of the probability distribution, you're gonna remove all those points in the middle that sort of you couldn't get, and so those are the supports that are associated to subspaces. Like you're not going to have a subspace of probability distribution of an open set without a point in the middle, right? That's not going to happen. And so that's where this idea of regular open set would come from. And so whenever we are going to define the measure that we had defined before, the state capacity and the fraction capacity, you are going to assign a value to these supports, to this lattice of subspace, and those are going to be regular open sets. And so that's going to give you a measure on the regular open sets. And then very quickly, I can just use directly the Carathédor extension theorem. I don't have to do any work, which is nice.
Yeah, that sounds good.
Right. I'll have to write down all this stuff and make sure that it works, and then meet again with Alex, and he's going to tell me whether it works or not.
Let's hope so. Or at least if it fails, then for interesting reasons.
Yeah, exactly. Yeah, I think I need to prove that the everything that we talked about before about the Boolean, what's it called? For the Boolean lattice, we needed the other property, which was
Distributivity?
distributivity. Yeah. So that's also something that I have to understand where it comes from. Because I will have it. You see, I have a bunch of. Now I'm kind of like futzing around, doing the research in the. So I had. Yeah, so these are all the things that I need to. This part actually is probably gonna survive without a problem because I don't care where that thing comes from. And from all of this, I had a bunch of, yeah. There you go. So these are my complement subspaces, and you see that the complement becomes an exterior, right? So the Boolean algebra here becomes an exterior here, which is exactly the Boolean algebra, what the Boolean algebra of the regular open sets are, and then the join. The meet becomes the intersection, which is exactly how it works for the again for the regular open set. The intersection of two open set is a regular open set, and the meet is going to be the interior of the closure of the union, which is again is going to be another regular open set because by definition I'm taking the interior of a closure. And so when you do the reclosure, you get the same thing, and you do the interior, you get the same thing. And so if all of this survives and all of this works well, then yes, I am putting, when I'm creating the measure, which should be here, and this was already the thing that one does when it does the I don't even need to do this because right now I'm defining this set on the topology. I don't need to define it on the topology. I only need to define it on the subspaces, which are the regular open sets. So, okay.
Nice. That's what more structure gives you.
Yes. Okay. So anyway, I'll need to do it, but I don't know what we're gonna do. The problem is what we're gonna do for the next live. So I'm also happy to just meet and futz around and talk about things. There are a couple of I don't know if anybody has free time. Probably nobody has free time anyway. But there is also some other things that I'd like to look at. there is so one of the open problems that I have is I need to put some type of symplectic structure on the set of ensemble space, on the ensemble space. And at some point, it dawned on me that I didn't want to put a symplectic structure, but I actually wanted to put a Poisson structure. And the Poisson structure is basically a Poisson bracket on the algebra, on the observable. So I have all the set of observables, and I put a Poisson bracket, and the Poisson bracket is going to give us something. And the observables in our case are the linear functional of the ensemble space. So it's something that you take you take an ensemble, it gives you a number, but they preserve the linear structure so that the convex combination of two ensembles, the mixture of two ensembles, the observable on the mixture is the average of the observable. And so on those things, I think we would like to put a Poisson structure. And I suspected that what's going to happen in classical mechanics, that would be the integral, when you make this Poisson structure, Poisson brackets between two things, then in classical mechanics, that's just the integral, the expectation of the Poisson brackets. And in quantum mechanics, it's the expectation of the commutator. And I found some people that do exactly that. And they do it though. Well, first of all, I don't think they have a superstructure, but that's the least of the problem. The problem is that they do it on sort of the state defined by the Hamilton-Jacob equation. So they don't do it on a probability of on phase space. They do it on a probability on configuration space plus the Hamilton, the Jacobi, no, the Hamilton principal function, I think it's called. And what I have to figure out is whether that is equivalent to a distribution over phase space, which I don't think it is, and whether if it isn't, we can like the method they have is still something that we can use. And so I don't know if it would make sense to get their book and sort of skim it through together. I don't know.
I mean, if you, yeah, we can try it.
Okay, now, we can try and see how it works. I don't know if it works well for Alive or not, but you know, I'm certainly game to try different things and see. And see. I mean, today was a disaster anyway. So.
Not really.
So we can try that because it's something that I want to do anyway. And even just saying, you look, at least I set up an hour and a half to do it. I'll, you know, we can certainly do it. And I can put the link both in, well, I can put the link certainly in to the book in.
Is it like a
Discord. Yeah.
free book, or is it something you have to? Like some of those are really expensive.
Good question. Good question. Oops. Tobias was not allowed to talk. Let me
Tobias talked
see.
earlier.
Yeah, but
I had to switch devices, but now
Oh,
it's
okay.
Thank you.
Okay.
Let me see. What is the name? Something. Did I put? I didn't put the link already in. Oh yes, it's the link that I already put in the chat in Discord. Ensembles on configuration space.
Here, I see it here. Yeah, do you have it pinned? You probably want to pin it. Just or if you can I pin it, probably not. If you go on the dot 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 right to the message, you can say pin the message. Then it's in the pin menu, so you can easily find it again.
Okay. Well, you know, it's fine. Okay,
Yeah.
I just didn't remember whether. Okay, so you probably can't download it, right?
Yeah, I should try that, shouldn't I? Let's see. Okay, it's a Springer link, and then you have this thing. Let's see.
Is
Is it available or not? Okay, I get a white page. That's not very helpful. Let's see.
on Google Books seems to work. Ah, no, okay.
Is it just a preview?
Yes, the preview. It's there is no what a pain this stuff. It's
Yeah, it's okay. That link isn't very helpful at the moment. Let's see.
yeah.
Entropic Physics by Ariel Chia. I'll just Google it and see what.
That is actually open. That's you know he has everything free. He's crazy like us.
I feel
But
like
the one that I was looking on was the ensemble on configuration space. But we can also look. So the one of Ariel starts from a very like Bayesian informatic theoretic way to justify things. I think he gets to math that is very similar. These people instead start the other people, Hall and what's the other name? Always forget. Reginato. I don't know how to pronounce it. I pronounce it like if he were Italian, but he's in Germany actually, and they basically just you know start with the idea. They don't um, like their motivation is we have something that follows the action principle, and that's it.
Mhm,
So they don't try to rederive things. They assume that they already have it. And so for my purpose, it makes it a little bit cleaner. What is their starting point? But I'm also interested in understanding what's Ariel's starting point. Uh, so
mhm.
that's absolutely fine. Or I could just have Ariel come and see if he wants to join the live and talk us about his stuff directly.
That would be actually super cool.
Yep.
Am I seeing that correctly, that both approaches like don't distinguish between classical and quantum?
Both projects work on similar structure, yeah. So that is, but it's kind of a little bit misleading because they don't really have like a common superstructure like we were trying. They typically have sort of there is the quantum side and the classical side, and they do similar things. At least Ariel, I know that he does that. Because he has a way to rederive the quantum and then he works on the quantum, right? When he's working on the quantum side, he's working on the quantum side. It could be that Hall Reginato, they do have a superstructure. I only skimmed up to the third chapter, and up to the third chapter, I didn't see it. Like they had different version of the same thing. But again, that's fine by me. I mean, if we can start getting the pieces to work on the two things and then generalize, it's absolutely fine. The thing that I don't understand of both that I still haven't found quite if it works or not is whether they are on the set of in the quantum case they are really on the mixed states or they are only on pure states or something in between. Again, it's my complete ignorance. I haven't looked at all these things, but so if you guys are interested, we could just say, okay, let's dedicate this time to figure these things out. It'd be fine by me. As I said, I have to do it because I need uh, I need the way that we're going to recover quantum mechanics is because we're going to have asymplectic or Poisson structure. That's how you recover it. I mean, this is how it works. So in classical mechanics, you have single decomposition, right? So if you have two pure states, every mixture of those two states can only be redecomposed in those two initial states.
Mhm.
In quantum mechanics, you have multiple decomposition, right? So the mixed state in the middle, right, can be decomposed by other states in the block sphere.
Yeah.
What's going to happen is the following. If you claim that you have two states and any of the mixture inside allows for multiple decomposition, what's going to happen is that all the mixtures are going to have to allow multiple decomposition. And this is just because if you take a point and you say, okay, this point is decomposable in these two other points, so you make some, so you have basically these 2 points here and these 2 points here, then because of convexity, you can now take these 2 points and make a triangle with the other. So you basically get a kite. And since you have the kite now, every point can be multiply decomposed. Right? So once you have you say, oh, I have a point in the middle that it's multiply decomposable, then you get everything has to be multiple decomposable. And now you say, okay, I will want some kind of homogeneity such that, for example, I can move points to points continuously, and every point locally looks like any other point. Right? You don't want to have if you had edges, you can say, oh, these 2 points are special, and so if you're going to impose some kind of symmetry on all those points, you're going to automatically get that the space is going to be an n-dimensional sphere. Okay, and now you say, okay, I have an n-dimensional sphere. I impose that the sphere has to be symplectic. Then it's a sphere in 3 dimensions. It's a 3-dimensional ball. There is no other choice.
Yeah,
And
that's
now,
that's the video you made recently about like how that defines 3 dimensions.
Exactly. It's the same argument, except that instead of being applied in the space of directions and only on the sphere, we are applying it to a spherically symmetric set of ensemble space. And that means you get a block ball. And now the fact that, again, you're going to have some notion of everything looks the same, it means that whenever you take 2 extreme points, you're going to be able to make a block ball. And I think that's going to be enough to basically say, yeah, then you have a projective, a complex projective space. Because that's what the complex projective space has. Like whenever you take 2 points, you're going to get a ball. So in the same way that the simplex has the property that whenever you get to extreme points, you have the line. In the complex projective space, you have the ball. So I think that's sort of how the extension work. And so there are going to be these 2 pieces, right? At one point, we're going to have to impose some type of homogeneity that basically tells you, essentially, let's say that the space at every point looks the same, right? That you can, for example, you can have you're going to have a group of transformations, and then you can move any points to any point, something like that. I still don't know exactly what is the right definition for that, but that's kind of what you need to have. And then once you say, oh, now I want to impose my notion of symplectic structure, Poisson structure, and we still need to motivate it and understand how we can get it from the physics. But assuming that then we have an argument, you put that argument in, and that's how you get quantum mechanics.
Nice.
And the entropy is going to be, again, another of those assumption of regularity. You're going to say that if I have an extreme point, and in quantum mechanics, I'm going to have extreme points because the way that you're going to impose, like one of the things that we're going to impose for quantum mechanics is that there is a 0 entropy. And so you're going to have states of a 0 entropy, and they all have 0 entropy. So when you're going to make this group of transformation that allows you to move from one state to the other, they're going to be deterministic and reversible, right? So they're going to be transformation that preserve entropy, and which is going to mean that all the pure states have to have the same entropy, and it's going to be 0 by definition, essentially. So what happens there is that the conjecture is that if you imagine to have the block ball, right? You can imagine to have X, Y, and Z as a coordinate, but you can also imagine to have the two angles and the radius. Now, instead of the radius, you can take the entropy, because the entropy is going to be an invertible function of the radius. Like every shell, whenever you go inside, you're going to increase the entropy. And so what's going to happen is that if you imagine the entropy as being one of the coordinates, and you try to make the Poisson brackets with the entropy, right? The Poisson brackets is going to tell you how that quantity changes under deterministic and reversible transformation. Well, the entropy is not going to change with deterministic and reversible transformation. Therefore, the Poisson bracket with the entropy is going to be zero no matter what other thing you put in. And so the Poisson bracket is killed by the entropy. The entropy and any invertible function of the entropy are going to be those quantities that always give you the Poisson bracket zero. In a Poisson structure, once you have these quantities, right? Well, in a Poisson structure, what happens is that the Poisson structure can be degenerate, not like the symplectic structure. Symplectic structure is never degenerate, but the Poisson bracket can be degenerate, and is degenerate because you find these quantities that when you put them in, they always give you zero. But then you can always find a set of quantities that kill the Poisson bracket that basically give you a foliation of symplectic manifolds inside the Poisson structure. And it should be that the entropy is exactly that quantity that if you take a foliation based on the entropy, you're going to get your symplectic structure. So if you have the pure state in quantum mechanics, you get the block ball. And if you start with a pure state and you do a deterministic and reversible evolution, then you're just going to circle around in the block ball. But that's going to be true even if you take a higher entropy. So you're inside a sphere in the middle. Then you're going to be rotating inside that sphere in the middle, right? You're always going to be rotating on the surface of a ball at constant entropy. And so that's the part that I need to generalize and figure out how it works. But it should be all connected in some sense. So that's why I say I need to sort of start looking at the work that they have and understand which pieces we can use. Because I really want to be able to define a Poisson structure on the ensemble space in a way that it's independent. And then depending on the state space, you can recover and say, aha, if I have more of this of information, I can write the Poisson structure on the averages as averages on Poisson structures on the pure states, essentially. That's sort of how it works. So I have a plan.
Sounds like a good plan. The specific way the entropy depends on the radius is probably like logarithmic or something, right?
It's a mess.
It's a mess? Okay.
Yeah. It's really a mess. Unfortunately, it's not a nice function. I think I've worked it out. I might have written it down somewhere, but it's not. It's like something like 1 plus r divided by 2 logarithm of 1 plus r divided by 2,
Okay,
minus, right? It's some stuff like that.
Interesting. I thought it would be like directly kind of logarithmic or something. That would have made sense.
Yeah, no, I wish it was that simple. But yeah, no, it was something that you like. It's one of those things that going from R to the entropy, you get a nice function that you can write, but you can't invert it. Like inverting it's hopeless. There might be something like there might be a good set of coordinates that it's not R that allows you to express things decently. I don't know how to do it.
I figured like that would be the easiest one because the directions wouldn't matter as much, right?
Mm. Another thing that it might be that while the expression is not nice, the derivative expression might be nice. I haven't tried that. Because if you take the derivative of the Shannon entropy, you basically get something like the logarithm plus one or something like that. So you get
Yeah, p log p, right? So then you get 1 plus, no, it's log p plus p by over p, so 1, yeah.
yeah.
Log p plus 1, yeah.
And so maybe the nice relationship are not between the entropy and the radius or the entropy and the probability, but the entropy, the derivatives will become nice. But again, I don't know.
That reminds me of something funny I recently learned, which is in quantum mechanics, the uncertainty principle cannot hold for any conjugate variables, for example, angle and angular momentum, because you could construct a simple extreme case where you have angular momentum like arbitrarily sharp, and then the variance or standard deviation for the angle would become bigger than 2 pi at some point. That makes no sense.
But here's the problem. Like the angle shouldn't be unobservable in quantum mechanics.
I guess, I mean, you could have simply an operator if you have some circular. If you just have a circle, you can define a position operator on that thing. So the technical resolution is that you derive it from from the commutator usually.
Yeah.
But the commutator is not defined on the whole space, and the states where you get this unphysical like violation, they are just simply not in the domain where the commutator is defined. And you can get something else. You can find another bound, but actually, then I realized it's not even so obvious how you take averages for angles in the first place,
That's
because
what I'm saying. That's why it shouldn't be an Hermitian operator.
I gotta check if they actually um like if they define an observable, check that it is self-adjoint, not just Hermitian. But anyway, even like classically, it's like how do you even like take averages of angles? Because
Yeah.
depending on whether you take 0 to 2 pi or minus pi to pi, that changes where your average is
Yeah.
and your variance. But then related to this, I found that people looked at this, how you properly take averages, and usually what you do, you put your directions on a circle,
Yeah,
an
exactly.
average of the vectors of these so
Right.
that it does not lie on the circle. And then you get basically a radius and an angle. And this radius is is usually defined in some way. So the standard deviation is then defined
The
to
variance, right?
radius, and that is a logarithm, just like you expected.
Okay.
Mhm.
So this is exactly the type of things where I think with the structure that we're going to have, we're going to probably even be able to talk about things on angles and so on. So, imagine again the block sphere, right? Every point you can have it with X, Y, and Z, right? Or you can have it with a direction, right? And when we are doing averages, right, we are actually taking convex combination. We are taking a point on the segment, right? That's basically the idea. So to have a property that is really something that you can think it as a statistical average, it needs to be linear with respect to that linear structure, right? And so X, Y, and Z, right? If you think it as a function of your ensemble space, they are linear structures, right? The angle is not, right? And that's exactly what you're saying. Like the mixture of two ensembles, right? If you make the mixture, it is not true that the angle of the mixture is the average of the angles, right? It's just not true. So if you take this and this, for example, right, and so you would have an angle here and an angle here. Now the average is going to be here, so the angle is there. So it's not even between the two. It's one of the two extreme points, right? And it's only when you have. So if you think about the way that you take expectation in quantum mechanics, right, you find that the expectation of your observable is the trace of your observables times the density matrix. And now, since the density traces matrices are linears, and the trace is linear, and the observable is linear, for every observable, you must have that the expectation of the mixture is the average of the expectations.
Okay, so would you expect that technically, so this operator for the angle is not self-adjoint and therefore not
So
a
now, if I'm working on the space of ensembles, right, I will have two types of quantities. One that are linear with the structure, right? And these are going to be things that correspond to statistical averages. And these are going to be the things that correspond to Hermitian operators in quantum mechanics and things that are the integral of something in classical mechanics. But once I have this set of points, right, I can use any value, any function that I want there, right? So I could define the angle on this, right? So I'm on the block sphere, so this is the state of ensembles. I can still define the angle inside the block sphere that actually corresponds to the average direction of my ensemble, of my spin ensemble. And what I was saying before, when I'm putting this Poisson structure, I can put this Poisson structure also on these variables that are not statistical quantities, that are absolutely not linear with respect to the structure. And I can write Hamilton's equation, right, on these things. And I get solutions, and I get equations of motion that actually work. I did it for the block sphere, because for the block sphere, if you think it as just a manifold on which you're doing the operation, and you're going to have rotation, so you're going to have an angular velocity, and you can write that down. So my hope is that when you're doing these things in the ensemble space, you actually have access to more, to more tools to work things out. And the angles are pretty bad typically in quantum mechanics because they're not observables. Even when you have a spinor, right, you have the boost of that velocity, right? It's not an observable also. Like you don't really have the only eigenstates of velocity that you have in spin 1/2 are plus c and minus c. Like everything else is not an eigenstate. It's because the whole thing is not a linear operator in that sense. And we should be able to instead, if you have the state, the state space defined by the spinors, we should be able to have a velocity on it and see how the velocity changes. Hopefully, finger crossed.
Okay, so just for me to recap. So I just checked, and you can define this angle operator just like a position operator, just multiplication on some L2 from 0 to 2 pi or whatever. And this is a self-adjoint operator. And also the angular momentum corresponding to that has some domain where it's self-adjoint.
Can you share
And we call this an observable, at least in quantum mechanics, right?
Can you share the link? I want to see it. Because for spin, I'm pretty sure you can't do it.
For spin?
Yeah.
Yeah, I definitely. So I have the PDF. I would need to find the link. Can I even put the whole?
You can just upload it, I think, if you want, in Discord.
For spin, you can't do it.
Let me see. Okay, I will put it on Discord. Yeah. That's actually my name for it. It's not the name of the paper.
It's
It's a pretty
okay,
fun
so
paper. So the problem is stated, as I said, that you get like a standard deviation bigger than 2 pi.
yeah,
That's above the
where is
resolution.
what is
Let
the
me see.
equation?
Page 41, that's 0.5. This is where they gave the resolution of why this happens. So I need to scroll down a bit.
Okay, so I'm page on 41, you said?
At the bottom there is 0.5.
0.5.
Actually, they
Oh,
just
you mean the pages are shifted. There's
Okay,
because it's page
yeah, 41 of the PDF and not
49.
Yeah, sorry, yeah.
okay, so where is the operator? I still don't see the operator.
Pi on Hilbert's
5
paper.
derivative multiplying by phi. That's the line you mean, right?
Multiplied by phi on the Hilbert space.
No, the reference some other section to say that this is all properly defined.
So this is the set of L square on from 0 to pi included, and then d phi. What is that d phi? What does that
The
mean?
change of the angle.
No, d-phi is just a measure on that space, like
Oh, the measure for the
yeah,
integration. Okay.
for the integral, yeah.
Okay, and hopefully you're gonna have a symmetric boundary condition, something like that.
Yeah.
Okay, but then
It's a complex eigenfunction. Yeah, okay.
the series of P. Yeah, I think we're talking about two different things here, though. Right, because this is, I have essentially a circle, I'm going around in a circle.
Yeah. It's not like 3D and you restrict yourself or something. No.
Yeah. So in this case, since you have something fixed, you might be able to do it, but
So I mean, once you move to a sphere, it breaks.
yeah.
Yeah, I mean, your coordinate system is not even well defined, no?
Well, so here's the point that the reason why the thing breaks is because it really depends on where you are when you're doing the average, right?
Yeah, at the poles you can't do anything anyway.
Yeah,
And
but it's sort of the averages when you're, if you take, so
oh,
let's
you
say that you're
mean
taking
yeah.
the average on the angle, what's it called? The latitude, right? This is the latitude, this is the longitude. I always forget.
I also always forget.
Yeah, so let's say that the one around the equator, right? So if you are doing an average on the points of the equator, okay, then you're probably going to have a single rule to be able to do it. But now you're mixing points on the equator and points a little bit up, right? And when you're making averages on that, the thing has to know about the other variables. Right, and that's where we are gonna bump into problems.
Yeah, I was basically just curious, like where we could find these problems, because about a lot of this paper, for example, is about just domain issues that you have because you cannot define unbounded operators on the whole Hilbert space
Right.
if you want them to be continuous. Um, and but that's why then you have restrictions on what is actually a self-adjoint operator. Hermitian is not enough because the domains need to match and so on. but then we still define everything that is a self-adjoint operator to be unobservable. So I was just wondering, I see obviously the problems with like even classically how to define averages of angles. And if you say I wouldn't consider this to be an observable, I was just wondering which structure
Yeah, no,
for me that
this
needs
is
to.
so this is again one of the problems is that it's only considering pure states. Now think about a mixture.
Okay.
Suppose that you have this done, okay? However, suppose that it works, that's fine. That doesn't matter to me, right? Now you have the circle, right? And you have an eigenstate here and an eigenstate here. And say that this is a 0 and this is pi, right?
Yeah.
Okay, now you make an equal mixture of 0 and pi.
Yeah.
Okay, I have an equal mixture of this. You take the average, it's going to give you pi halves.
Yeah.
There's nothing at pi halves.
Okay, but then just to be clear, like structurally it comes like it depends on another structure on the mixed states and being linear in the ensembles, okay? This
Right,
is not covered by only like being a self-adjoint operator on like pure states.
right. The
Okay.
fact that it's self-adjoint on the pure states means that when you're going to do average in statistical mechanics using the trace and mixed state, you're going to have the average.
So wait, so it is covered by the fact that it is self-adjoint.
Yeah, because you're making the trace of the operator times the density function. These are kind of the problems that sometimes I see when people are trying to do these things, that they look at a specific mathematical problem for one thing, like, you know, the domain of the operator and so on. But there is a bigger context in which that thing that you're trying to find has to work. Right, so this is the same for when you know, you take the half line and you find the momentum is not a self-adjoint operator on the set of all on the Hilbert space of those things, right? And then you try to do some other things and so on. The point is that that might be one problem, but you might also have a bunch of other problems, and you have to solve all the problems.
Yeah, I mean, actually, so in this paper, I appreciate that he gives like examples. This is just the appendix. The core is like showing that quantum mechanics is like mathematically consistent.
Mhm.
If you take care of all the domain issues and so on,
Right.
because otherwise you can like write down almost anything and
Yeah.
it makes no sense. Um, but no, I forgot what I wanted to say. Okay, I forgot. I don't know. Oh wait, so about the half line.
Yeah.
So if I define my momentum operator
Mhm.
as some generator of translations,
Yeah.
actually I don't know how to define like translations on a half line because where does all the stuff move if I move to the left?
Yeah.
So would I even expect that there is something like momentum if I don't know what it means to translate wave functions on the half interval?
Yeah, it's you know, yeah. How does how would a Hamiltonian? Yeah, it's yeah.
But then it wouldn't be physically so unintuitive to when the math tells me actually there is no momentum operator or not. Like it's not that bad.
Right. Then the question is, what is the you're going to have a conjugate variables and a conjugate variable, and what is the conjugate variable? Because
Because
if
it's
you
still a
imagine,
position operator?
hmm?
Okay.
Well, if you think about um, what's his name, a two-dimensional space, right? Two-dimensional space, you can chart it with these two variables, angle and radius, right? You can make that transformation.
Yeah.
And so in principle, that exactly give you these two problems. One, you have a half a line for R, and
Mm.
you're going to have a circle for theta.
Mhm.
Okay.
How do you make that coordinate transformation? I don't claim to know. But the point is that you have a real a space that you know how things should work, which is the X and Y, right? You know how things and momentum are going to be defined by X and Y. And so yeah, I don't know exactly what's gonna be the corresponding things, but maybe you shouldn't think about. I mean, maybe the fact that the two operators that are conjugate are linked by the fact that one is the generator for the other. Maybe that's not the thing that survives, coordinate. I really don't know. I haven't.
Okay.
Wouldn't that also be part of the difficulty why like general covariance doesn't fit with quantum mechanics?
That's another problem that I have because, again, statistical averages are not relativistic. So you have a position, right, at a point, and you move the point, that's fine. But when you have statistical averages, right, again, the issue is that you're taking the statistical average on the linear space defined by your coordinate. And so if you have different coordinates, you're going to have a different way to calculate averages, right? If you are in X and Y and you just take the average of the two things, you're going to find, I don't know, the middle point. Let's say that you do one half of both position in X and Y, you get the middle point, right? If you do it in R theta and you do the same operation, you take the average R and you get the average theta, you don't get the middle point. You get something completely different, right? And again, this is connected to the same thing, right? Because at the end of the day, if you think about, well, I'm going to have a statistical distribution of this, even just in classical mechanics, I have a statistical distribution, I change coordinates, the averages do not transform with in the same way that the coordinate do. And now you say, okay, in quantum mechanics, I should think of really the pure states as in some sense, some probability distributions, right? Because at the end of the day, when you're taking the expectation of X, you are taking a statistical average. What's the proper way of thinking about these things? I really don't know.
I think if you would know, then the whole issue would go away. Like suddenly you could unify the two big things.
So the way, again, that I'm trying to skin the cat, because what is it? I'm trying to avoid some problems so that I can solve the general one, and then we can figure out what. So if I think that instead of having, the points and making statistical, I start with the idea that I have ensembles, right? Then I know that there is a special class of the variable quantities and so on, which are the ones that the value, the quantity on the statistical mixture is the average of the quantity, right? So those are special quantities because they respect the linearity that is given by the ensemble. And in a sense, even those are, I suspect that things like, what's it called? Inertial frames and stuff like that, and Euclidean coordinates and the diagonalization of the metric and all these nice things are giving you, oh, these are the nice cases because that's where you can get and do statistical averages nicely.
Yeah, that makes sense.
And I think that's really ultimately what it comes down to. And for any other thing, then what's going to happen is that the linear structure that you have on on the real value that you've picked as variables, because the value of variables are still real numbers and they have a vector space structure, is not exactly the same linear structure that you have on the ensembles, which is where the real physics is. And therefore, you need to have some of this correction. And so your structure is not really nice and linear as it should be, because they are not in the proper coordinates, but you get some of this distortion and nonlinearity and so on, right? And my hunch, which could be completely wrong, but my hunch would be that the real linearity is given is there in the statistical mixture, and you always are going to have a vector space there, and everything is nice. And then you have some representation that you can use. Some of them are nice and linear, and some of them are not. But you can still, at least locally, transform to the linear structure of the ensemble, do the calculation there, and then go back.
Yeah, from what I saw, that going back part is quite difficult. Like there are some definitions for that stuff, but they're not like, they don't respect round trips, basically.
Well, right. So as I said, like this is a very high level view, and one, it might be a fail, and two, even if in principle you can do it, it doesn't mean that it's easy. In the same way that in GR, right, you might have a set of coordinates and you calculate you have a metric and you calculate the curvature, and the curvature is zero everywhere. So you say, then I should be able to find a transformation of coordinates that makes everything flat, and mathematicians tell me it's not that easy sometimes. Like sometimes it's even impossible. So
Yeah, I mean, you could have like a toroidal universe or something. Is that the issue?
Yeah. Like the topology is not straightforward, right? So that yes, you know that you're flat, but you still have a weird topology, and then still finding even a local set of Euclidean coordinates. It's not that easy. So this is when I took GR many years ago. The professor was saying this. So the fact that you know that in principle that there is a solution to the problem doesn't mean that it's easy to find a solution or that you even can. So, so that's basically, Tobias, the way that I see this. And again, the sort of the key to me was when I started thinking about Hermitian operators, not just as things that I apply to wave functions, but things that I apply also to mixed states. And then it was clear that in that case, that linearity comes from the fact that you can make statistical average. Like if you basically say, oh, I want an operator, right, that it's linear with respect to statistical mixing, you are going to have a Hermitian operator. Like a Hermitian, because it's gonna the quantity is real, but you're gonna have a linear operator.
Yeah.
Because the trace is linear, and you're gonna have a addition. The mixture becomes a linear operation in terms of the mixed state.
Yeah. Okay.
Now, doesn't mean that this stuff is, this way of defining the angle might still be useful for some things, right? That doesn't preclude the fact that it might still useful, but I think you're going to have problems once you apply it to mixed states. Anyway, it's getting late, and we're basically we're fetzing around. I'm happy fetzing around. It's just that it's probably impossible for people to that are watching the live. But anyway, shall we end it here? So next week we'll try. I can try reaching back to Ariel and see if he wants to join us. If not, we can either look at his book or the one from Hal Reginato.
Yeah, that would be great.
Interviews are well, interviews, I guess, I don't know, discussions with experts, I don't know, are always great.
Yeah, I'll see. I wrote him like a couple of weeks ago. He didn't write back. Maybe he's busy. We'll see. All right, see you guys next week then.
Yes.
This next week, bye.
Bye.